Hello, sir. Good evening.
Good evening. Good evening. Can you hear me well?
No, sir. Your voice is coming little low.
Hello. Just give me a second. Give me a second.
Okay.
Okay, is this better? Can you hear me better now?
Yeah, sir. It's good.
Okay. Okay, great. Thanks, Pranjal. Do we have anybody from the MLT instructor team here today?
Yes, Nitin this side.
Oh, Nitin is here. Okay. Is Karthik also here?
Yeah, Karthik will join in few minutes.
Okay, great. Okay, great. So maybe we'll get started while he joins. So welcome everybody to this live session here. So as you know, I am Arun Rajkumar. So I've been handling this course, but then in a in an online mode so far. So I think it might. I mean, the main purpose of this session is just to catch up to see how all of you are doing with respect to this course. If there are any questions, queries, general comments, feedback, suggestions, anything that you might have at this point. I know your final exam is due in a week from now, or less than a week. I'm sure all of you have seen all the 12 weeks of content and would have several questions and queries. So we thought we'll have a live session to just address those if there are any. So the way we can do this is if you can uh, raise your hand in Google Meet, and then I can call out the names of participants, and then you can ask your questions. So in the interest of time also, I would request all of you, if there are lots of questions, I would request all of you to ask one question, and then if there are more hands, we will go to other people also, and then come back to those who have already asked a question. Okay. Yeah, so maybe we can get started. Pranjal, if you want to go first.
Yeah. Hello, sir. Good evening once again. So my very first question is that means we have seen two W's. Okay. One W. By W I mean the vector which we used in supervised learning as well as unsupervised learning. So in supervised learning, basically we have used it means like coming to unsupervised learning, we have projected it. Okay, means the point onto a W, and in supervised learning we have used a W as a coefficient. So is there any relation between these two W's? Means like I'm pretty confused. Means like going through all the lectures.
Okay.
Means is there any relation?
Okay, so let me rephrase your question so that it might, so that I understand it properly. So you're saying, let's say in PCA, we were given some data and then we wanted to find a direction, which we called as W, and we found a direction by projecting data onto this direction. In linear regression, which is a supervised learning problem, also we are trying to find a direction. So now, what is the relation between what the directions that we are getting in PCA and the directions that we are getting in linear regression? Is that a fair way to
Exactly.
rephrase the question? Okay.
Yep. Yep. Exactly.
Okay. Okay. So I think I might have to um, use some pen and paper to make this clear. So I unfortunately don't have a notebook here today. I mean, the tablet here, but I do have a notebook. So I'm going to kind of move to the notebook view. Just give me a second. I'll do that, and then we can try to do some writing. Let's hope this idea works. Okay, so how does this look? Let me begin myself so that I know what I'm writing. Okay. Okay, is this flipped?
Sir, can you use Google Whiteboard is available, right? We can use that one also.
But it'll be. I don't have um, a tablet right now, so it would be hard perhaps for me to write. So let me try once again to see if I thought the video was flipped. Um, hmm, okay, so what is this? Okay, just give me a second. I'm going to log off for a second and come back, and hopefully that will fix the problem. So you're still seeing this in the opposite direction, right? Flipped version of this. Hello.
No,
Can you?
sir, it's right.
It's correct.
Yes, sir. HELLO. Yeah, from
Oh,
left.
you're able to see it. Okay, excellent. Okay, so for some reason I am able to see my own screen in the flip mode.
Okay.
That is fine. As long as all of you are able to see it, it's fine. Okay, so
So, sorry, sir, if you could just move to the left a little bit.
like this.
Good evening, sir. Yeah, now it is better. A little bit more, sir.
Okay.
Yeah, now it is clear, sir. Thank you so much, sir.
Okay.
Good evening.
So let me do this. Um, okay. So the question, just to rephrase the question again. So the question is, you have an unsupervised learning problem like PCA, where we find a W, and in linear regression we find a W. Are these the same things, different things? If so, why are they different, and how are they different? So here is the way to think about this. So let's say we have some data points as PCA in the standard PCA world, let's say something like this. Now, all my xi's are in R2. These are two-dimensional data points that I have. And what PCA finds is two lines, W1 and W2. One in this case with where if the direction in which if you project, you will have the maximum variance, and the other direction where you will have the minimum variance, right? So let's say this guy was our line, which was W1, which we got by maximizing the variance. Now the confusion of Pranjal is the following, right? So if you have another data which is a linear regression problem now, where I have x and this is y. Now note that x is a real number, not two-dimensional data, but y is also a real number, which is always a real number. Now the question that is being asked is that, well, can I just, now if I look at how x and y are, they also look something like this. Let's say now, now I do a linear regression and I get a W that also looks something like this, right? So now, are these two guys the same W's, or is W1 and W2 different? Right. So this is the question that is being asked. So the first thing to notice here is that this is an unsupervised problem where all your data points are in 2 dimension, right? So let's say this is height, this is weight, and you have 2-dimensional data. Whereas here, it can still be height and weight, right? So there's nothing stopping these two things to be height and weight, but this is 1-dimensional input with which you are trying to predict y, which is weight, right? So you're using height to predict weight. Now here is the thing, right? So now how are we finding this W, saying that this W is best, versus how are we saying this W is best, is fundamentally different for PCA and linear regression. The reason is quite simple, right? So if you have a bunch of data points like this, now for every direction, right? So I can pick any W. Now I'm going to measure goodness of that W in an unsupervised setup first, and then in the supervised learning problem, I'll take a W and measure its goodness in the supervised learning setup. Now, in the first thing, in the unsupervised learning setup, how can I measure the performance of a W? If I give you a line and a data set and I ask you how good is this line with respect to this data set, the way you would do is you would project all the points onto the data set, right? And then measure the sum of the lengths of the projections, which is, this length plus this length and so on, right? So these lengths. So this is what you sum up over all data points and you'll get a number, and that number tells you how good is this W for this data set. That is what we care about in PCA. Whereas here in regression, that's not what we care about. What we care about is, if I have this line, then what I'm saying is that, for this height, this is my prediction, right? So this is, let's say height is 100, this is height is 125. This line tells me what is the y value corresponding to each of the x input, right? So for this height, this is the prediction. For this height, this is the prediction. But what does the data say? The data says this is the value here, maybe this is the value here, and so on and so forth. Maybe there's another point here where this is what I predict, this is the actual answer. Now, how do I measure goodness of a line? In this case, well, I will measure it by measuring this vertical distance, right? So this is what I predict, which is W transpose X, and this is Y. And then I look at the difference between these two and then square them up, right? So it's a vertical distance that I'm actually, vertical deviation that I'm caring about, because my prediction minus the actual answer squared is what I care about. Here, I am trying to find a line such that if I look at proxies along this line for these points, then how much do I lose, right? So that's what I'm trying to find out. So the proxy is by definition, the shortest distance is this perpendicular distance, whereas here this is a vertical distance, right? So though these two things look similar, they might actually be they might be slightly different also in general. That's point number one. Point number two is, so fundamentally, this is unsupervised learning, this is supervised learning, right? So which means that here you have d-dimensional data, here you have a label along with the d-dimensional data, right? So which means that if I have height and weight, if I want to predict height using weight, if I want to predict weight using height, it is not true always that you can just think of that as an unsupervised data with one additional feature, which is y, and then do PCA and then get a W and then use that somehow to make predictions for the supervised problem, right? So those things are not at all equivalent, because you are measuring goodness of a W in differently for these two problems, right? So does that make sense, Pranjit?
Sir, again means I want to counter this, means like if in supervised unsupervised learning we are finding the minimum error by projecting it perpendicularly, means why we are going for this one means like in this second scenario of supervised learning, this is increasing our error because this is not a perpendicular line which is like minimum.
Okay. So the reason is for in supervised learning, y is special. In unsupervised learning, neither height nor weight are special features. Here, weight is a special feature. You have to use height to predict weight. Your goal is to do well on y. Here, that's not the goal,
Okay.
right? So
Okay.
you might have 100 features, but then if there is a label, you want to predict the label well in supervised learning. So that feature has to be used specially, right? So you have to combine your other features to get this feature right. That's what your task is, right? So you will have to do it differently with respect to that feature only. Does that make sense?
Yep. Yeah.
Sir, just a quick clarification. Isn't both the distances perpendicular distance, sir?
No. So this is the perpendicular distance, right? So if I fix a line and then ask what is the distance of a point to the line, well, that is what PCA is measuring, right? So there are two distances, right? So this and this. This is what PCA cares about. This is what regression cares about. This is not the shortest distance, right? So to this line. But then if I use this line to make my prediction, this is what I would predict, but then this is what my answer is. So the difference is what I care about.
But in case of regression, sir, the gap between predicted value and actual value
Mhm.
is just a dotted line from this W, right? So that turns out to be a perpendicular minimum. It seems like that.
What is perpendicular? So this one,
Yeah, that
that is
yes,
perpendicular to what?
on W, on my regression, on my line of regression. Yes.
How can this be? This is vertical, right? So
Okay.
anything perpendicular is going to be in this direction, isn't
Okay.
it? Yeah. Okay, great. So let's go to the next question. Mr. Vasu, if you want to ask your question. You are muted.
Sorry, I just unmuted myself. Yeah. So when it comes to SVM, or actually not just SVM, but in case of taking SVM as an example, there's a primal problem and then there is a dual problem, right? And we use Lagrangian to formulate the dual, and then we use strong duality to flip min max. We do that entire thing to arrive at the dual, right? Then we try to simplify the dual and we end up with, let's take in the case of soft margin, we end up with alpha t minus half of that entire equation, right? Y transpose, X transpose, X, Y, and alpha, right? So where is, which the primal is clear, but where exactly, which one is the dual? Is it just the initial formulation before we flip, min max, or the final one is the dual formulation? Which one is the dual is a little confusing for
Okay.
me.
So after you do flip the min max, whatever you get is the dual. Now, in this particular case, we can further simplify the dual to eliminate one variable and then just retain max. But in general optimization terminology, the min max is the primal, the max min is the dual. Right. So in the
Okay, okay. Because in the final, in
go ahead.
Go ahead.
No, I was just saying in the case of SVM, we have the dual simplifies further, and we get a max over alpha, right? So in general, it has to be like this, right? So max over alpha greater than 0, min over W something, and now this guy is quadratic, and then you can take the gradient set it to 0 and substitute it back. So this variable gets eliminated. We know how for every alpha the solution is, and that is not true always, right? So in general, we will call this the dual problem. If this has an analytical solution, then the dual further simplifies where the min goes away, right? So that is also a dual problem. It's exactly the same problem, right? So
Okay. So okay. So I have just a connected question.
Yeah.
See, in the primal, the number of constraints are very clear. There is a alpha and there is a epsilon or zeta, whichever one we want to call it, right? In the dual,
that's a W and an epsilon.
Sorry.
That's not an alpha. W and an epsilon in the primal.
Yeah. Sorry, W and an epsilon, right? Then in the dual, see the simplified form, we just have, in fact, we don't even need beta. We just have alpha here, and that's all, right? But in the dual, do the constraints, will they remain the same, or there'll be lesser number of constraints?
So the constraints will double, right? So so the dual. So this is the hard margin dual. In the soft margin dual, the constraints are going to be 0 less than or equal to alpha less than or equal to c, right? So which means that every alpha now has to satisfy two constraints. One, it has to be greater than 0. One, it has to be less than or equal to c. Earlier, it was just alpha greater than or equal to 0. Now you double those constraints. Right? So
correct, but compared to the primal, will the constraints remain the same? For soft margin, it should remain the same, because even for the primal also, it is W and epsilon.
right.
Here it is again alpha, which has 0 and c. It has to fulfill those. But so the number of constraints don't change, right?
Number of constraints with respect to what?
With respect to solving the optimization problem.
No, when you say don't change, it doesn't change with respect to what?
The number of constraints.
Yeah,
the
yeah.
absolute number of constraints.
So yes, so still the question I'm asking is, so here you have, you know, 2n constraints if you have n data points, because every data point has an Lagrange multiplier, so that has two constraints. So these are 2n constraints, right? So that is the this is so now the question that you're asking is, earlier this was just n constraints, right? Because you only have alpha greater than or equal to 0 for every value. Now the upper bound is also a constraint, so it has doubled.
Okay. But if we see the primal formulation, it's again 2n number of constraints.
The primal is so okay. So that depends on how we write the primal, right? So I mean, okay. So if you just write the primal as okay, so you can write the primal as min over w psi
epsilon.
Epsilon. Okay, half norm w squared, such that w transpose xi yi plus epsilon I is greater than or equal to 1 for all I, right? So this is the constraint. So this is one constraint for each data point, which involves both of these guys, yes, w and psi. Right? So
and then epsilon greater than 0.
Yeah, that is also there. Epsilon greater than or equal to 0.
Yeah. So no, I was just wondering, does the dual help in kind of reducing the number of constraints we are operating under? It doesn't.
It doesn't, right? It's still do it.
Yeah. Thanks, Prof.
Sure.
Sir, sorry to interrupt here. Epsilon is greater than equals to 0. It's a feasibility here.
It's a feasibility constraint. That's correct. Yes.
Okay. Thank you, sir.
Yeah. Because you don't want to pay negative bribes, basically. Yeah. Sorry, I should say this. Okay, Arun Mohan, you want to go next?
Yes, sir. Sir, here in that equation, how when c is equal to 0, w is equal to 0?
In this equation, okay,
Yes.
Good. Okay, so if c is 0, okay, so now let's ask the question: what would happen if c is 0? If c is 0, this guy is not there, correct? So I can equivalently write my problem now as minimize. Oh, are you able to see that? Maybe not. Okay, minimize over w half norm w squared, such that w transpose xi yi plus psi I is greater than 1, psi I greater than or equal to 0, and psi X. Right? So now let's say these constraints were not present for the moment. Let's say these constraints were not present. So then what is the smallest value of half norm w squared that you can get?
0.
Yeah. So with w equals 0, you will get half norm w squared is 0. So that is without the constraints. Now I am imposing some constraints, extra constraints here, right? So it cannot suddenly become anything. I mean, the best guy cannot suddenly become less than 0, right? So now if I can show one way to achieve 0, then that has to be the optimal. Would you agree?
Sir, can you repeat that part, please?
Yeah. So what I'm saying is that if I hide these constraints, right? So then it is very clear that W equals 0 is the solution. Now I'm claiming that even if I don't hide this, even if I introduce these constraints, if W equals to 0 is still the solution, right? So then that has to be the optimal for this, because I mean here, you know, I am adding extra constraints and still saying I'm getting the same value as what minimum value as what I could have gotten, right? So constraints means the problem is becoming typically harder, which means that the minimum should typically go up. But then if I can demonstrate that even after adding these constraints, the minimum does not go up, right? So it will be 0. It is as good as the unconstrained problem. Then it has to be that has to be the optimal solution, right? Would you agree to that? Is that reasoning okay so far? Or should I repeat it again?
Like what you said makes sense. Even if you're adding or deleting constraints, it doesn't make a difference.
If it doesn't make a difference,
Okay,
then that has to be the optimal solution, right? So
yeah.
So without constraint, right? So this is the entire space of W's, let's say. Now without constraints, I have found that W equals 0 is the solution. Now, I'm introducing these extra constraints. If I can still argue that W is, feasible, first of all, then, it will definitely be optimal also, right? So for this problem.
Yeah.
So now I'll try to argue why W equals 0 will still be the solution. Now for every W, how are we measuring its goodness? Well, that is the objective function, which is just the half norm W squared. Now for W equals 0, what I am going to set is, what are these guys? These guys are going to be, for choice of W equals 0, these guys are going to be 0.
Correct.
Now I'll set epsilon I equal to 1 for all I. Of course, it satisfies feasibility. Now I can set epsilon I as 1. It satisfies this condition also, because 0 plus 1 is greater than or equal to 1. Now, how much am I paying in the objective? Well, half norm W squared, which is for this W, it is 0. Right? So by setting epsilon I equals 1 for all I have satisfied the conditions. And for that W, I pay half norm W squared, which is 0. So now you cannot show me a different W with less than 0 objective value. Right? So because this is the smallest. So this has to be the optimal, right?
So one follow-up question to what I asked. Sorry, Divya, just one question. It's connected to what we were having in the class yesterday when W was actually equal to 0.
Mm-hmm.
The discussion came up as what exactly is the positive space then? It was the entire space that is positive. Then what penalty is to be paid?
By what? By each data point?
When we say epsilon I is equal to 1,
Mm-hmm.
epsilon is where we are actually paying a bribe. Why do I need to pay a bribe when the space is complete? Complete dimension is mine. Why do I need?
What do you mean complete dimension is yours?
If W is equal to 0, what represents what does it mean was the question that was coming up, sir. So if W is equal to 1 then we know it is going in the x1 1 and x2 1 direction, that is 45 degrees, and then perpendicular to that is where my boundary line actually stays, correct? Yeah. So if W is equal to 0, then what does it mean? It was the question that we were discussing yesterday.
Yeah.
On that stage, it was about the entire space being the positive space, correct? So if entire space is positive, then why do I need to pay a bribe? Because epsilon I, you set it as 1, in which case the condition is satisfied. But my question is, why do I need to pay a bribe if everything is okay?
If everything is not okay, because I need a margin of 1. If the entire space is 0, but then I get a margin only of 0, right? So
okay.
I need a margin of 1. That's what I'm asking for each of the W's. Right? So to achieve margin, I need to pay the bribe, right? So you might have to pay the bribe even if W is not equal to 0. There might be a case where W transpose Xi Yi is 0.5, which means I'm correctly classifying that data point. But then I'm not happy. I'm saying you have to classify it with margin of 1, which means that I still have to pay a bribe of 0.5 to get the condition satisfied. Right. So here every point will have to, to satisfy the margin condition, it has to pay a bribe. So you are absolutely right if I had set this to 0.
Right.
Right. So then I'm fine. right? So W equal to 0 is a feasible solution. It doesn't have to pay any bribe. That's perfectly fine. In fact, I would actually, nobody wants to pay any bribe here, so I'll be happy actually, right? So I'll give that as my answer. But now I have to force data points to have a margin of 1, so which is when that won't be a good idea unless we increase the bribes.
Thank you, sir. Thank you. Divya, sorry to have interrupted. Yeah.
If I can just continue on that thought, I'm struggling to visualize what does it mean to have W is equal to 0. I mean, how does the classifier work?
The classifier would just say 1 for every data point. If our convention is sign of W transpose X equals 0 means 1, right? So which means that there is no separation between negatives and the positives that is possible, and so you cannot get a margin at all, right?
Yeah, essentially, like in principle, the SVM, like the problem doesn't exist anymore, or there is no solution actually. There's no viable solution in a way. Could we say that just as a
What do you mean
not
viable? So there is no viable.
in the sense that it's not doing what it's supposed to do. It doesn't classify plus and minus 1 anymore.
Well, yeah. So by convention, it will say everything is 1. It would do, right? So by just, it would say do that by just predicting 0 for everybody, and then our convention says that's just 1, right? So there is no way that it's going to do well.
Yeah. Okay.
Sorry, I don't know if Divya had a question. Otherwise, Ganga Prasad.
It's just in this regard, if we're eliminating the C, that means we're not penalizing for the bribes, right?
Precisely. Yes. Yeah. Exactly. That's why you should not set C to be 0. Is what I'm saying. Right. So you are not penalizing the bribes, and so I am happy to pay a bribe of 1 to satisfy the margin condition, and so I will make W to be 0. But then that's a useless thing, right? So we should not be doing that.
Okay. Thank you.
Ganga Prasad, please go ahead.
Yeah. Good evening, sir. Am I audible?
Yes, you are.
Yes, sir. Sir, I have a question related to some of the concepts which have come across all the algorithms. I think one of them is kernel, like starting with kernel PCA, then kernel clustering. Though we have not covered kernel clustering, then regression, kernel SVM everywhere, right?
Yeah.
And I appreciate the fact that you have covered in deep tour something in detail about kernel, but somehow I am missing some dots and I'm not able to connect it completely, sir. Like how data points are getting transferred and then they are becoming linear and then kernel matrix and all. So it will be really better if you can throw some light on that. And similarly, if time permits, then something about norm, because norm, when here we are talking about in all objective function, it is norm square, and we are calling it an L2 norm, right?
Yeah.
So some more insights about norm. That's all, sir.
Okay.
And then, sir, I will not ask any other question. I have just a small request, sir. Towards the end of the session, just block 5 minutes, sir. I have some general question related to way forward, sir. Thank you, sir. That's all from my side.
Okay. Thanks, Ganga Prasad. So let me answer the norm thing first. Okay. So norm is just a way to measure lengths, right? So if I have a vector space like this, and then there is a vector like this, 1, 1. Now I want to somehow say what is the length of this vector. Now you can measure. Now, okay, so mathematicians would care about defining properties of what a good length function should satisfy. What is a length function? Think of this as a length function. You input a vector, out comes a number, right? So now, of course, there are hundreds and thousands, infinite functions which will take a vector and then output a number. Sorry, I don't know if you see that. Yeah. Hundreds and infinite functions which will just take a vector and output a number. So among those, we want, if you want to say something is length, then we want those functions to satisfy certain nice properties. So now, for example, if I take the vector 0, 0, 0, 0 or 2-dimensional 0, 0, then if I push it through the length box, I should intuitively, I want this to produce 0 as the answer, right? So I don't want the vector 0, 0 to have more than 0 length. So that is one property that I might want, right? So I also want length to be always non-negative. I don't want negative lengths, for example, right? So that might be one property. The other property is what is called as triangle inequality. So it would say the length of A plus length of B should be less than or so if I take two, if I take two, then they should be greater than or equal to. So let me say it this way: the length of A plus B should be less than or equal to length of A plus length of B, right? So this is sometimes called as the triangle inequality, right? This again comes from your Euclidean geometry, basically, understanding Pythagoras theorem, triangles, and so on and so forth. You might want something like this. So now mathematicians would then ask, well, what are the possible functions that satisfy these three conditions together?
It also has to be commutative, in the sense length AB should be B.
AB should be?
Length between A and B should be equal to length between B and A. That also is a condition, if I'm not wrong.
Yes, I think, yeah. So you want length of A minus B equals length of A, B minus A. That's what you think. So one way to say that is that you can say length of minus A is same as length of A, and then you can, that would give rise to that.
Yeah. No, actually, you misheard me. I just mentioned as kind of more general form. I just said length A comma B should be equal to length B comma A. I mean, whichever way I measure, it should give me the same number, same length.
I see. Okay, so that is okay. So yes, sure. You mean the ordering of the coordinates should not match?
Yeah.
Okay. Sure. So now what? So now the question is, what are the type of functions that satisfy these, basic properties that you would want length to satisfy? And it turns out you can come up with infinite possible functions which satisfy this. Our intuition, the basic intuition based on our Euclidean world, right? So we see world, we measure things, and we understand things in a certain way, we sense things in a certain way. So that would say simply that if I want to measure the length of 1 I would say that it is how much, this is 1 1, this is 1, so this is 1 squared plus 1 squared, and then I take a square root, right? So now Pythagoras theorem would say that this is square root of 2, and then I would say that is my length. But now that is not the only way to measure length, right? So you can measure length as, for example, the sum of the absolute values, right? So sum of the absolute values of, if I have a d-dimensional vector, the sum of the absolute values of each of the coordinates. This will also satisfy all these conditions that we are looking for, right? So and then there are so many other things as well, right? So you can think of this as a P, and then say 1 by P, right? So this is also in general. This is also called as this. I mean, this is also a valid length function. So now we give names to these length functions. One of the functions that we have seen is what is called as an L2 norm, which is our usual way to measure length. So if you have A1, A2 till AD, then we will say that the length is square root of sum over I equals 1 to I, AI squared. This is our usual Euclidean geometric way of measuring things. But there might be other ways to measure length also, right? So for example, when we saw lasso, we would see that we measured length like this, so on and so forth. Now one other way to think about this would be to say that, um, if you ask where are the, in 2 dimension, if I'm measuring length using Euclidean way of measuring length, and I ask, hey, where are the guys with length equals 1? So then they will all be somewhere in this circle. Whereas if I ask this is norm of x equals 1. Now if I ask in the L1 sense, where are the data points where the length is 1, then that might look something like this. Now there are other ways you can possibly measure length as something like this, I guess. This would give you what is called as an infinity, L infinity norm. So this is just max over I absolute value of xi. This can also be shown to have desirable properties. So this is called as L infinity norm, right? So L for length and 2 for what power we are essentially using in this sum over I equals 1 to d ai power p square root of 1 by p. Which p we use, that will give us different choices of lengths basically.
Sir, the what you've written to the right is not visible. Thank you.
Yeah.
So what does P stand for here? Sorry, I missed it.
P is the L. So this is called as an LP norm. P, if P is 2, then this is our Euclidean norm, L2 norm. If P is 1, this is our L1 norm. So on.
Okay, no specific name for that, right?
I don't know if this is as this as
Okay, okay, no problem. And then kernel was there, sir.
okay. So this is the norm. So I hope that is clear. Kernel. Okay. So what? Okay. So you are trying to understand kernel and why it might, why things might become linearly separable in a higher dimension. Is that what we are
Yes,
asking?
sir. Some general understanding because it seems to be extremely powerful. It has come everywhere, starting from PCA to SVM.
Yeah. Yeah. Okay. So simplest way to understand this is to say that you know um, you can take any uh, polynomial equation. Let's say you take a quadratic equation, which is ax square plus bx plus c um, equals 0. Uh, then I already see that this is not or let's say this is f of x. Uh, what is the question exactly? The question is to just guess, just give a feel for what kernels are, right? So that's the question. Yeah. So if I have ax square plus bx plus c, this is not a linear function of x, right? But we can think of this still, if I think of this as a function of x, it's not a linear function. But if I have a function g, right, so which has input as not just x, which is a single number, but then let's say x, x square and 1, which is a three-dimensional input, then this function is just, what it is doing is it is taking the vector, in this case b. Let me make this x square, x and 1, so that we are consistent. So let's say this is a, b and c uh, times x square, x1, right? Oh, sorry. Yeah. So basically what I'm saying is that you have this function, which is a quadratic function of the input. Now what I'm saying is that change that input to not just a single number, but then certain other things that you derive from that single number. Instead of saying x, I now say x squared, x and 1. I give you three inputs. Now what you do is just linearly combine these three inputs: a times x squared plus b times x plus c times 1, which is ax squared plus bx plus c. So a quadratic relation becomes linear if I map my input to a higher dimensional space. If I think of this as a function of simple x, then this is a quadratic function. But if I think of this as a function of a three-dimensional vector, x squared, x and 1, then this is a linear function. That's all there is to kernels. So now, because we know several algorithms which work well in the linear world, now even if you have a non-linear boundary in the input space, can I convert my data to a high dimensional space, and then in the high dimensional space I can do a linear, uh, I can learn a linear classifier, for instance, in the case of supervised learning. Uh, Now, so this is just a single number, right? So, but in practice, what we are going to have is that we don't have a single feature, right? So we'll have multiple features. So let's say we have d features, and so you collect height, weight, age, gender, whatnot, right? So you collect 100 different features. D is 100, let's say. Now, what you can do then, now if you want to measure, if you want to kind of do a quadratic relation among these 100 features, let's say you had height, you had weight, you had whatever, I don't know, salary, you had three different features, let's say, right? So now what would be a quadratic function of these three features? So if I just have x, then this is my quadratic function, right? So now if I have three numbers, then my quadratic function is going to be, a times height into height squared plus b times weight squared plus c times salary squared plus d times height into weight plus e times height into salary plus f times weight into salary plus some constant, right? So this is going to be the general form of a quadratic function if I have three features. So which means that if I want to capture this now in a as a linear function, then I should have height squared, weight squared, salary squared, height into weight, height into salary, weight into salary, and 1 as my features. Instead of giving height, weight, and salary as input, now I have to create a new data set where I have height squared, weight squared, salary squared, blah blah blah. There's so many larger number of inputs, right? So height, weight, salary uh, will become height squared, weight squared, salary squared, height, salary, 1, and so on. So now the number of, so this is initially in D dimension. Now you want to map it to some, you want to measure, this is quadratic, which is two-dimensional polynomials, second degree polynomials. But then if you want a general pth degree polynomial, then from D, you will have to go to something like order of D to the P, right? D power P dimensions. So in a world where computation does not matter, you have the superpower to run your algorithms with as large an input feature as possible, then we don't need kernels. We can simply say that if I want to capture a pth degree relation among my features, I will map my d degree, which is, let's say, d is 100, my p is, let's say, 10. Now if I want to capture 10th degree polynomial relations among my 100 features, I won't work with my original features. I don't care. I won't just use height, weight, and salary. I mean, I should add actual height, weight, and salary here. Those things should go height plus weight plus salary. Anyway, so I won't use my original 100 features only, but then I'll map it to 100 power 10 dimensional features, and I'll run my SVM there, and I'll run my logistic regression there, for example, right? You can do that. If you have enough computational power, then you don't need kernels. Now the problem is this is super big, right? So 100 power 10 is so big that we cannot really maintain computationally. It's going to be super expensive to run these algorithms. Now then we notice that is there some property of the algorithm that can help us get away with actually creating this 100 power 10 dimensional data set and then running the algorithm? Can I somehow get away with that without creating this 100 power 10 dimensional space? And yet, is it possible to run the algorithm? Now, for several machine learning algorithms that we have seen in the class, now if you go back and revisit these algorithms, you would realize that what you really need is if I have x1 till x thousand data points, each of these data points are in 100 dimension. Now I could map this to phi of x1 to phi of x thousand, and each of this is in 100 power 10 dimension, and then run my algorithm. But then what my algorithm really cares about is not necessarily the individual data points, but then how they are pairwise related. What I really care about in my algorithm is phi of xi transpose phi of xj. I can express my algorithm only in terms of the dot product between the data points, right? So if I had originally run the algorithm with this, what I would care about is xi transpose xj. If I map it to high dimension, then I only care about phi of xi transpose phi of xj. That is, if somebody gave me phi of xi transpose phi of xj for each pair of items, data points, then I'll be able to run the algorithm, right? So that's all I need to run the algorithm. I don't need the data points, but I only need the relation, pairwise relation among the data points. If your algorithm has this property, then we are saying that then it means that if there is an easier way to compute phi of xi transpose xj, phi of xj for each pair of items, without explicitly computing phi of x1 to phi of x thousand, then we are in a good situation, right? So because we will directly go from here to here by sidestepping this computationally expensive step. Now, kernels allow you to do this. Right? So the goal of kernels is to say that if I evaluate my kernel at 2 points xi and xj in my original feature dimension, right? So remember, these are R100, this is R100. Now this is going to give me a value of 10, let's say. This function, it is, what is this 10 actually? This 10 is, I have mapped my 100 dimensional data to 100 power 10 dimensional data phi of xi, this xj to 100 power 10 dimensional phi of xj, and then I take a dot product here, right? So that value is 10, right? So this is basically a shortcut to directly go to phi of xi transpose phi of xj, and that, in some cases you can efficiently do that using a kernel. Yeah. So now if you go back and look at what kernels are from the course, I think you should be able to follow it better.
Sir, I have a counter question here.
Yeah, right.
Okay, so at the end of kernelization, what we did was means like we have a modified step 3 in which we eventually computed xid, means like uh, x points. Okay, so from those x point, how we gonna get w?
Oh, okay. So which algorithm are you talking about? In general?
Means kernel PCA, means we take means very first algorithm kernel PCA.
Yeah.
In kernel PCA we have step 3, means we step 3 which was modified, and eventually what modification was means we took xid, means like we took basically projection of phi xi transport w k. So we, as a data point, we took the projections in higher dimensions, those projection. So from those projection, how we gonna calculate W?
You cannot calculate W, right? So if you want to calculate W, then you need phi of xi for each of the data points, right? So you will not
Okay.
be able to calculate W. I mean,
So
yeah.
so the point xid, what these xids are? These are just projections, right?
I don't know what you mean by xid, but I think you are
Means alpha ij sigma j is equals to 1 to n alpha ij kij. This is what I mean by.
okay. So what you get is, a bunch of alphas.
Yeah, alpha and then kij is corresponding to them.
Yeah, kij is corresponding to that. So we don't. I mean, we will not compute. So if you want to find W, then using alphas, you will have to do the following, right? So alpha I. So if I want WK in kernel PCA, then I will do alpha IK times phi of x.
Yeah.
If I really want to compute W, this is what I should do. Now this is super expensive because I don't want to do this, because if we want to do this, I want to do phi of xi, which is precisely what I'm trying to avoid, right?
Yes.
So I don't
Yes.
want to do this, so which means that I will not do this, right? So now, but what I want is, if I take a data point xi, now in the high dimensional space, it has become phi of xi, right? So let's say like xk. In the high dimensional space, it has become phi of xk. Now, so this is R100 in our notation. Now this is R100 power 10. Of course, I can't calculate this, but now I have found if I have the superpower to calculate everything, I would calculate phi of xi, wk. Then I can do phi of xk transpose wk. You see the dot product between my high dimensional data point and w, right? So that would tell me how important is, how phi of x wk in representing phi of xk, right? So I basically what I will do it. So okay, w, the notation is messy, so let me not call this k. So let me call this xl. This is phi of xl. So I will take the lth data point and project it onto the kth principal eigen direction. That would be phi of xl transpose wk, right? So phi of xl transpose wk. This is what I want to do, right? So if I had the power to compute phi of xl and wk, then I would do this. But I don't have the power to do this. But I mean explicitly, but implicitly I can still achieve this, right? So because what is this dot product? This dot product is just phi of xl transpose sum over I equals 1 to n alpha I k phi of xi, because this is my wk. This is
Yes.
simply saying this is just sum of I equals 1 to n alpha I k phi of xl transpose phi of xi. Now this, oh sorry, this I can compute. How can I compute this? This is just k of xl comma x.
After this step, after this, we are taking means like all the keys in here, right?
Yeah, right.
As a data point.
Correct.
Okay.
That's correct.
So what does that represent? Means like this is just a higher dimensional projection, right?
This is just a higher dimensional projection. So this is telling me how correlated is my high dimensional data point phi of xl with each of the principal components in the high dimension, right? So that is what this is telling me. So I'm saying so you can represent xl, then basically instead of xl, now what I will do is I will take the top k principal directions in the high dimension, and then I will do, basically this is what I want to do.
Okay. These are principal directions.
These are principal directions, right? So because your alphas did not, alphas are special,
Okay.
right? So alphas came from the eigenvalues of the kernel matrix, so this would be principal direction, right? So I mean, whatever these principal directions are, I want to take the dot product with those principal directions after I do the mapping to high dimension. Now what I'm saying is that you can still achieve this without explicitly computing phi of xl and w.
Yeah.
It's just alphas.
Okay. Okay.
Okay,
So
thank you.
these are my new data points.
These
So
are your, yeah.
now these are become my new data points, and means like I can next from now onwards I can perform anything from with these new data points.
Yeah, you can do
I got your
classification
point.
if you want.
Yeah.
Okay, thank you, sir. Thank you from my side also, sir. Sir, just to in norm itself, any specific reason for choosing L2 norm in all our algorithms?
So one of the main reasons of choosing L2 norm is because it is differentiable, mathematically very convenient. You can take the gradients. Often you get analytical solutions. But if you do the L1 norm or the infinity norm, then it won't even be differentiable. So we won't get closed form solutions, right? So that is the reason why we always start with L2 norm. That is one reason. The other reason, statistically, if you want a reason, then the right way to think of this is that whenever we are doing a regularization using L2 norm, it corresponds to thinking that our errors are somehow Gaussian distributed. And Gaussian is very natural. It's the most natural, if you don't have any information about the error, and if you think that the error is just, some average of a bunch of random fluctuations of things that you don't have control over, so then it will almost always be Gaussian distributed. So you can think of regularization as equivalent to a Bayesian world where you are putting prior on W's using Gaussian. That's also one other way to think of it.
Okay, thank you, sir. Let me open for thank you.
So, thank you, Ganesh.
Sir,
Manoj,
sorry, a follow-up on kernel. Sir, in this we are assuming that the relationship is linear in some higher dimension, right?
yeah.
But is this an assumption or is it just a fact that every relationship would be linear in higher dimension? And why did not we go with with some algorithm which fit a non-linear relationship in the real dimension? Like,
Okay. So, so the first question is this linear in higher dimension? That's the hope, right? So if you choose a kernel, so here is how you do it, right? So I choose a kernel. Once I make a choice for the kernel, it means that I'm making a choice for how I am going to map my lower dimension to high dimension, right? So to which, for instance, if I choose a polynomial kernel, then what are the features that I'm actually computing from my data points? If I have height, weight, and salary, if I choose a polynomial of degree 3, then it means that I'm not satisfied with just height, weight, and salary. I'm going to create new features which are height squared, height cube, height into weight squared, all those things, right? So your choice of kernel immediately fixes what is the higher dimension to which you are mapping. Now you don't necessarily know that once you choose this kernel, it's suddenly going to be linear your classification problem will become linear in this high dimension. You don't know that, right? So that is something that you will have to somehow cross validate and figure out which kernel works best for your data set. So it is not necessary that always things will become linear. Of course, if you use a polynomial of degree n, where n is your number of data points, then everything will become linear in such a high dimensional space, right? So, but that would basically overfit in some sense, right? So you won't do well on your test data. That is the first part answer. What was the second part?
So second part was why did not we go with some algorithm which fit
Ah,
a non-linear relation?
we are doing that, right? So I mean, okay, so here is the intuition, right? So you want a nonlinear classifier in the input space, right? So I have two-dimensional data. Something like this, and these are zeros. Let's say something like this, and these are pluses, right? So all these are plus ones. Maybe they're extending further so that it's not linearly separable necessarily, right? So you want this classifier, right? So this is your best classifier. Oh, sorry. This is your best classifier that you really want to achieve, right? Now, what we know is all these algorithms that we develop, we know that they can only produce lines, right? So we cannot run, I mean, we can run our algorithm. There's nothing stopping us from running a soft margin support vector machine with the input features as such on this data set. I mean, you will get perhaps some line like this, right? So you will get something like this. Now, what that tells you is that basically, actually, you want a nonlinear boundary, but then you are assuming that my boundary is linear. But if you know for sure that it's going to be non-linear this way, right? So then um, your question is, why don't I directly try to find some algorithm that gives me a non-linear boundary? What I'm saying is we are doing that in an indirect fashion. The way we are doing that is that instead of searching for a non-linear decision boundary here, we are saying, what is this line is linear because W transpose X equals some constant, right? Which means that W1 x1 plus W2 x2 plus dot 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 WD xd is some constant. Now, what is this line? This line is a nonlinear function, which means that it is W1, let's say x1 squared plus W2 x1 x2 plus W3 x3 squared is constant. Let's say something like that is this nonlinear line. So this is a nonlinear equation that this decision boundary satisfies. But if I think of this as, instead of x1, x2 till xd, if I have x1 squared, x1, x2, x3 squared, these are also as part of my features, then, with respect to these features, it is still linear. So which means that we can find nonlinear boundaries, decision boundaries in our decision space, if only we had these extra features. Right, so instead of the original x1 and x2, if I have x1 squared, x2 squared, then, well, this is just a linear function of those features. But we don't have those features. Now what we are saying is that use a kernel to get these additional features, and then run your linear algorithm there, which would correspond to a nonlinear decision boundary here. So in fact, what we are doing is finding nonlinear decision boundaries. Does that make sense?
Yes, and just for the first part, so you are saying that in real practice we do first find different kernels and validate them on the data set, and based on the accuracy you choose the right kernel function. Is that right understanding?
Yeah, you would cross validate for the kernel.
Yeah. Okay. Thank you.
So just to
In
follow.
practice, sorry, I'll just ask and you also ask. Need not be answered immediately, but in practice, do we deal with non-linear classifiers at all? Because linear, linear functions are easy to handle. They have a lot of good properties, so on and so forth. But do we really activation functions are non-linear? That's clear. But in general, do we have non-linear classifiers as such? I'm not like, even if there is an equation which is non-linear, you convert it to transform the variable such that it becomes linear, like log transformation, so many other things. But do we ever use non-linear classifiers as a group of, like, as a family of classifiers? Do we study and do we use them at all?
So we are right. So I mean, whenever you are using a kernel, it means that implicitly you are using a nonlinear classifier. Though you are performing linear operations, the non-linearity is kind of subsumed in the kernel evaluation. Right?
Correct. So I think I'm saying the same thing. Probably I need to phrase it better, which is we are converting that into some form of linear structure so that it's easier to handle, or
Yes.
whatever is the reason. But without that, like, directly, do we deal with non-linearity? Are there algorithms which deals with non-linearity, or it's not, like, it's too difficult, so we don't ever study them that way?
It is too difficult, meaning it might be too computationally difficult, right? So I think, I mean, in the early 1970s, 80s, people were doing polynomial regression for linear regression, right? So where they would actually, which would mean that you are actually creating these nonlinear features and then doing least squares on that, right? So that there is nothing stopping us from doing that as long as you can efficiently do that. It's fine, right? So that's one way to get a nonlinear classifier. The other way, supervised, that's a regressor. But the other way would be to do things like ensembling, right? So you can do bagging, boosting, which we have also seen in this course, where though your weak learners might be simple decision trees, or even simple, perceptron type classifiers, whatever you want to use as simple weak learners. Now, once you combine them, then they'll become nonlinear classifiers. Again, you are not directly, I mean, to answer your question, we are not directly modeling a nonlinear relationship and learning the parameters, simply because, to make real sense, you might need high degree polynomials and then the parameter space will blow up. So typically we don't do that, but all of these are different ways to sidestep that direct difficulty.
Okay, thank you. Ravi, over to you.
Yeah, thank you, sir. So it's not very different from or far from what Vasu has asked. So if we were to actually geometrically represent, or rather graphically, if that were to be possible to see the data points in the 10-dimensional space, the data points themselves will be linear. Is that correct? They will not be occupying the parabola kind of a thing, but they will be all be in a straight line.
They will be linearly separable. That's what I say. They need not be linear, right? So they will be linearly separable.
Okay. Sorry. Yeah, got it.
Yeah.
Got it. So they will
They may
practically
not,
be, yeah.
yeah, go ahead.
If like what you had represented in the graph here, the two parabolas, parabolically, if we were to assume that as somewhere distribution around a parabola, these parabolas in reality will become straight lines in that dimensional space.
Yes.
Okay. All right. Thank you. That's all it was.
Sir, I have a question. So, it is related perceptron. So basically, in perceptron, we have one mistake. Uh, uh, we have classified mistake. So I have a doubt that what this mistake is. Is this a mistake? Uh, Means like we can make, or is it a mistake which is allowed?
Um,
Uh,
okay, neither, right? So it is a mistake that you are making. That's all, right? So you are currently maintaining some W at some Tth iteration, Wt, and then
okay.
you see a point xi comma yi. Now, if you are a good W, then you would actually predict this guy correctly, right? So which means that sign of Wt transpose xi would match yi, assuming yi is plus or minus 1. If not, then it means that if I stop my algorithm here and I use this W as my W, then at least in this training data point, I'm making a mistake, right? So now
But
that, yeah, go ahead.
but we have a bounds on mistake, right? Means like if it is neither, means like it is not allowed mistake, or it is not a mistake we are doing. So means like if, how we can bound anything, means like if it is not, where we gonna find it, or currently we are in use of it.
I didn't understand that question.
Sorry, so let me rephrase it. So, like, uh, we have a bound on a mistake. Okay. So,
Well,
if
What do you mean we have a bound on a mistake? The number of mistakes that perceptron makes.
Yeah, number of mistake the perceptron makes.
Correct. Yeah, we have a bound which is something like r by gamma r squared by gamma square. Right. So it won't
Yeah,
go
ours.
beyond more than this. Yeah.
Okay, so this is a bound. Okay, so this particular bound means at tth iteration we have these many number of mistakes. Is it saying this thing?
No. So what I'm saying is that if I run my perceptron algorithm, right? So and then every time I make a mistake, I update my W. Right. So
Okay.
I find a data point, I make let's say that data point was not correctly classified my current W, then I'll count that as a mistake and then I change my W. Then I'll find some other data point, it's not correctly classified, I count that as a mistake, change my W. I keep doing this. Now what I'm saying is that the number of times I'll count cannot increase more than r squared by gamma square. The number
Okay,
of
number
mistakes,
of times I count.
correct. So I might make the same mistake on, I mean, I'll make multiple mistakes on the same data point. That is also possible. But the number of mistakes I make in total cannot exceed r squared by gamma square.
Okay. In total, the number of mistakes on a particular data set cannot exceed this thing. Okay.
Correct.
Yeah, got it. Thank you. All clear. Yeah.
Yeah, Manoj. Oh,
Can
sorry.
I go ahead? Sir? Okay.
Sorry, yeah, go ahead, Vasu. If this is related to this question, otherwise we'll come back to you.
No, it's not to do with this. It's to do with regression and pseudo inverse.
I'll come back to you then. Yeah.
I have a question on the PCA, sir.
Yes, please.
So before doing the PCA, do we get the information on whether the data is linear or not to go for kernel? How do we know?
Okay, so one way to, so there is no one single way to exactly say we will always know it, but one reasonable way to say we can know it is if you do linear PCA, standard PCA, and if you observe that your error as a function of number of principal components that you should use, if it decreases like this, right? So as a function of this, then it means that as you add more and more uh, you know uh, uh, principal components, of course the explained variance or the error with respect to the subspace spanned by these principal components is going to go down. But then if it goes like down like this, then it means that essentially you have a low dimensional linear subspace. But if
Okay.
it goes down like this, then it means that perhaps you are missing non-linearity. You are kind of trying to pretend some manifold like this is where the data points is, but then we are trying to map it to linear subspaces. So we are kind of thinking of these as actually noise, whereas that might actually be the structure in the data, right? So while plotting the eigenvalues of the covariance matrix, you will get a fair enough idea if it's a good idea to do linear PCA or
Okay.
go to cluster.
Okay, thank you. There is one more question. It's a general question, sir.
Go ahead.
In week 8, we are talking about the generative story of the data, but I thought in machine learning we just only analyze. Do we also generate? If so, then in which situation we do that kind of thing?
Uh,
Generating the data?
no, so so there are several situations where you may want to generate data. For example, you might have some missing features, right? So where you want to fill those features with the most probable value. So you might have a model which you're training from data, and then if you get a new feature data point with some features missing, now you can fill in if you have a generative model, right? So if you have a discriminative model, I don't know what is the process that generates X. So there is no, probability that I'm associating with every value of X, right? So I cannot really use that. So generative is one place where you can fill missing data in a more principled way. That is one thing.
Okay. So
Yeah.
it's not just only analyzing the
Can
data, right? Machine learning. It's also we generate the data and then.
Go ahead, Uma, finish up. Sorry.
Yeah, I'm done. Yeah.
Yeah. Sir, I have a connected question, which is, I just wanted to clarify if the concept, if you understood it correctly. So, see, if you take, I'll just take a simple example of real example to kind of contextualize it. For example, let's say I am figuring out through some data modeling whether should I give a loan to a person or reject a loan, right? And I have some data, and I could have the salary, age, designation, education, all that kind of stuff, and credit history, so on and so forth. And then I create a model, right? And then let's say afterwards I get some data, new data, and I kind of look at the model and say, okay, these thresholds are fulfilled, or this is the likelihood of this person defaulting or not defaulting. So I accept or reject the loan application, right? Here, the way I've structured this, it's straightforward descriptive model in the sense that I have some data, and based on that, I'm saying, should I give the loan or not give the loan, right? Now, in case when we move to, is that clear, sir? Did I explain it well?
Yes, yes.
Yeah. So now, when it comes to the generative side of the story, here in this case, I don't know anything about the data itself, right? I mean, what is the, like for example, salary is a variable, a feature I'm using. I don't know really how many people have, let's say more than 10 lakhs of salary in the universe, right? Or how many people have a credit score of 700 plus in the universe. I don't know such information. Whereas in generative, when I'm doing this, for example, knife based, because I know the probabilities of, how many people in the universe have, let's say 10 lakh plus salary or 20 lakh plus salary, or have a certain credit score, or have a certain level of education and above, right? Is that what generative actually means, in the sense that I know more about the data itself, hence I can enrich my modeling. So let's say that I know that only 0.1% of the people have, let's say, 20 lakh plus salary in the universe. That means it's very unlikely that they will default, right? Because they will be probably in the top 0.1% of the universe. Is that what generative is? And not just like for example, missing values, imputation, and all that, but is that what the real power behind generative modeling is? That I know a lot about the data itself, hence I can enrich my modeling fundamentally more than just descriptive. Is that a correct way of articulating it? I just want to check that.
Yes, yes. So though your goal is to discriminate one class from another, if you have more modeling assumptions or more reason to believe that your data comes from certain distribution, the features come from certain distribution, or the class conditional features have certain distribution. For example, in the loan case, for people for which y equals 1, for whom the loans are given, I might have some sense of how the histogram of the salaries are going to look like, as what you're saying, right? So if I can incorporate that into my model somehow, then two things will happen. One is that if my modeling assumption is correct, then my accuracy will improve. The second is that if my modeling assumption is correct, that will, in some sense, trade off for the need for more data. Even with less data, the model is already telling me more information. So even with less data, what I can achieve with a generative model, I would be, I mean, I can achieve what I could achieve with a discriminative model where I might need more data, right? So because in some sense, in an indirect way, it is telling me that, I'm putting more structure on what the X distribution is. So I might not necessarily, need so much data to estimate it well. Right? So that is one way to think of this also. What essentially, I mean, the bottom line is whatever you are saying, it is going to enrich my data modeling, where I can do better even with less amount of data. Right? So that is
okay. Okay, thank you.
So may I ask something on what you said a little earlier about the eigenvalues, and from there trying to understand how the manifold is going to be, or is it a straight line? I mean, straight plane like that? Is it something which I understood correctly, that from the eigenvalues we get an understanding of the structure, underlying structure?
We will get the understanding of whether the underlying structure is linear or not, right? So meaning we'll get a feel for whether there is really a low dimensional subspace where most of the data lives in, but then has gotten corrupted with some error, right? So if that is indeed the case, then your so let's say this is some k bar, which is like maybe 10, but then your actual dimension might be 1000. But then with this itself, if your cumulative, I mean, the amount of eigenvalues that explain the variance kind of is more than 95%, then you already know that the rest is perhaps error. Right? So of course you cannot conclude 100% with anything, but that is enough indication to say that The data lives in some low dimensional subspace like this. Ideally it should have been like this, in which case all the remaining eigenvalues, if it's a 3-dimensional data, but then if it lives in a 2-dimensional subspace, all the third eigenvalue is going to be 0. But then if it is slightly corrupted with noise, right, so it increases, decreases a little bit, then these errors will add up and give you the third eigenvalue, which will be much smaller when compared to the first 2 eigenvalues. So you can conclude that the data lives in a 2-dimensional subspace, though these are 3-dimensional data. But then if it falls down like this, then it means that all 3 dimensions seem important, right? So if I miss 1 dimension, then the amount that I will suffer seems to be large, right? So maybe the data points are like this. Now, I would not really call these data points as they are in 2-dimensional plus some corruption. I should not really be calling that, because these corruptions are not really corruptions. They have significant mass.
Mhm.
So that would reflect in the third eigenvalue, right? So in which case it will fall down linearly.
Okay, got it, sir. Thank you.
Yeah. Arun Mohan. Sorry, I don't know if you are there, but if you are there, you're muted. Maybe it's not there. Manoj, you. Oh, yeah. Go ahead.
Yeah, sir. What is the role of regularization?
What is the role of regularization? Okay, so
Overview.
one way to think of this is to say, sorry, yeah. So one way to think of this is to say that I have some belief about how the final solution should be, and can I incorporate that into my optimization problem, into my algorithm, right? So which means that if my solution is away from what I believe, then I should somehow penalize that in my optimization problem. So regularizer, as the name suggests, it's trying to regularize, right? So it is making my solution regular, where regular is depends on whatever I think is regular. If I'm using an L2 norm regularizer, then it means that I believe that W's which have small length are the regular ones. W's with large lengths are irregular ones. That's what I believe. If I believe that, then I would use that to regularize my problem, which means that whatever my loss, whatever loss that I have with respect to the data points x comma y comma w, now I'll add half norm w squared, and then I'll minimize over this over w. I don't know if you're able to see that well. Yeah. So this would be my optimization problem. Without the regularizer, I'm just caring about the loss. Squared loss could be hinge loss, doesn't matter. But now with the regularizer, I'm saying something extra. I'm saying that, hey, I'm going to penalize for W's which are not regular. What are not regular? The ones with large length, right? So now what is regular is completely up to what we care about, right? So how we are trying to think about the problem. In the SVM case, this became the regularizer because this corresponded inversely to margin. The smaller the length, the larger the margin. So we want W's which we think are regular having large margin, and so we will regularize with half norm W squared. Right. So that was the SVM connection. But if you look at a simple regression problem connection, this would mean that we want the solution W to have very, very small values, right? So, but then why would natural question is, why do we care about that, right? So now, when it would actually help is when, you have a lot of redundant features or a lot of, highly correlated features, right? So then you can express your output Y in multiple different ways, right? So if I had height as a feature, height, weight, and salary as a feature, and if I had again somehow I made a wrong measurement and then I repeated and I got more heights, weights, and salaries as features, then I don't want my W to put weights on all of these, right? So I want to kind of pick and choose only the important features that will explain my Y. So I'm saying initially, I don't know which ones are useful, which ones are not useful. Now I can look at every subset of features and then try to run a regression model and then see which ones gave me the least cross-validation error, let's say, and then I can go with that. But then if I have 100 features, I have to use 2 per 100 subsets, and that's simply not going to be possible. So this is an indirect way to say that, well, initially I'm going to say all W's are, all features are useless to me, which means that I'm going to think of all W's as zeros, which means that I would I want, this guy is minimum. I mean, if there is no loss, then I'm kind of preferring W equals 0, which means that I'm saying all features are useless. Now let the data tell me which features are useful, right? So if the feature is really useful, then the first term will become small for that feature, right? So whereas, I won't add unnecessary features here, because if I add unnecessary features, this guy is going to go up, the norm is going to go up, right? So somehow I'm saying, if you have a lot of correlated features, then forcing you to push a lot of unnecessary features to smaller values is the aim of doing this regularization. Now, why would you have a lot of correlated features, right? So if I'm just having height, weight, salary, maybe they're correlated, maybe they're not correlated, right? So it's a question that one might ask. But then let's say if you're doing a kernel regression, then you're introducing new artificial features, right? So that's what the goal of a kernel is. You had height, weight, and salary. Now I'm introducing height squared, height into weight squared, weight into height squared, all sorts of relation, which means that these new features that I'm introducing will necessarily be correlated, right? So I'm introducing correlation by introducing non-linearity also. So now I would rather regularize it so that I don't really need to use all these features. In a high dimensional space, I don't want to use all features. I will regularize it and let my loss decide which ones are important. Right? So that's the reason why we do regularization. The reason why we do this way of half norm W squared and not something else is because this is mathematically convenient. Right? So you can take the gradient, set it to 0, and things will work easily. But nothing is stopping us from doing half norm 1. And we know that this is the lasso problem, right? So this will give you actually, the W values will get pushed to 0 and so on, which we saw. But the idea is that overall you want to penalize W's which don't fit your understanding of what W should be using a regularizer. Does it make sense, Arun?
Yes, sir, got it.
Yeah, Vijaya.
Yes, sir, thank you.
Vijaya, yeah. Sorry, we can't hear you, Vijaya. Vijaya Yuvaram. Hello.
Hello, can you hear me, sir?
Yes, now I can hear you.
Yeah, sir, I have a question.
Yeah.
So whenever we see, if we have a unknown data set and we want to see a cluster, the data set as a cluster, most of the blogs, they suggest you should run a PCA and you will see a cluster in it. But in PCA, we are doing only two things, right? We are looking for variance and then we are looking for compression. But why is PCA suggested to find clusters in our data? But is it a good thing?
So PCA won't find clusters in your data. I don't know which blog is talking about that, right? So you might do PCA and then run a clustering algorithm on top of it, right? So but PCA cannot find clusters, right? It's just going to find you alternate representations for your data.
Okay. So if I run a PCA and then if the points get bunched up together, is it good to say they have same property?
What do you mean property?
Okay, so if I run a PCA on a supervised data set wherein I have their labels also, which class they belong to, and then if the points which belong to the same classes they bunched up together, so that it does say something about their underlying property, right? So
Okay, so I understand what you're saying. So basically, you're saying, is it a good idea to run PCA before you run your favorite classification algorithm?
yeah,
Is there a way to say that? In practice, people do that all the time, but there is no guarantee that if you do PCA and then run your algorithm, it's always going to do better than not doing PCA, right? And running it with raw data. The simple reason is as follows. I mean, if it was always true, then we would be doing it, right? So,
Sir, if I can just, sorry, I didn't understand the question. Are you whoever asked the question? Are you saying you run a PC on the features first and then run the clustering, or you also include the labels?
okay. While running PCA, I will only include the features, and then if the transformed features, that is, if I plot the PCA 1 and 2, and then I visualize it, if the points tend to be closer together, does it say something about those points? So can I go ahead and conclude
Oh, I see.
person 1 and person 2 are closer in this PCA plot? They have the same property, or they come from the same, they have the same property or something. Can I conclude?
So it would mean the following, right? So if you do PCA and then just maybe you have 1,000-dimensional data. Now you did PCA only for the features and then visualize the 2-dimensional data, and you observed that the 2-dimensional data looked nice, right? So maybe these were the points where the ones which had now if you color it with labels, now let's say these were the points which had label 0, these were the points which had label 1, then that indicates to you that for the purposes of classification, if you cared about only saying discriminating the zeros from the ones, then you can conclude that the top two features given by PCA are enough. That is what this is saying, right? So if you want to run classification on this data set, then it suffices to just to use 2 features instead of 1,000. But this will rarely happen, right? So I mean, if you do PCA with just 2, I mean, this means that in some sense there are 2 directions which are enough to your represent your data points, not 1,000. But you cannot do this for 5 dimensions, right? So what if you needed 5 dimensions? But you will not be able to visualize that, isn't it? So so that's so then the question is, should I do PCA or should I not do PCA before running my favorite classification algorithm? Now that depends, because what is PCA doing? Again, let's take the simple example. Let's say you have data points like this, and you project it like this, points like this. Let's say you will not be able to visualize these for the moment, right? So you cannot look at visually and then conclude what is good, what is bad. Let's say we are in that world. Now you project these things here, and it so turns out that these are pluses, these are minuses. If it happens like this, then yes, you can do PCA and then work just with the projections, which means that maybe this value will just get a value of 5. This is 5 times the unit vector in this direction. Maybe this will go to a single number 6. This will go to number 10 and so on. Maybe this will go to -1 and so on and so forth. And then you will be able to do classification well in this, if this is how your labels are. But it's not necessary this is how your labels should be, right? So now adversarially, this direction is something that we have ignored in this whole process, right? So we are saying that this direction is error, right? So we are calling this error, and PCA is going to ignore this direction. Now remember, PCA is unsupervised. It is not looking at the labels to figure out whether this direction is error or not. But for the purposes of discriminating with respect to the labels, this direction might be very important, right? So in the same data set, maybe this is my data set, now these might be plus points, these might be minus points. Maybe, oh, you will see that, yeah. So maybe this is my data set now, right? So these are the plus points, right? These are minuses. Now if I do PCA, I would kind of project all these guys in this direction. The pluses and the minuses have gotten mixed up in this direction. Whereas if these are all plus, these are all minus, my W should be in this direction, so that I can actually use this as my classifier to say everybody on this side is plus, everybody on this side is minus. But then the direction itself is lost in PCA. So in words, if I have to say this, what I mean is that the direction that you throw away as error in PCA might be very critical for classification. We don't know that a priori, right? So PCA doesn't care whether you're going to do a classification task later or not. It's going to do the best thing that it can do, right? So in that sense, we should not really be using PCA technically, before you apply classification algorithms, but people do that all the time because it is unlikely that what PCA thinks as error may be needed for classification, but you cannot really conclude one way or the other for sure. Right? So does that make sense?
Yeah, sir. Thanks.
So can I ask a question, sir?
Yes,
So
sir.
I have two questions from PCA. So one is, sir, I have a confusion from the day one that PCA should start finding the best fit line, or it will do the eigenvalues first using the data set itself. So what is the first? It is randomly choose the line, or it will choose the eigenvalue using data set covariance, calculate the covariance matrix, then calculate the eigenvalues, and then do the PCA.
So why do you think that it might do something random?
Sir, because sir, in the because it will minimize randomly, just like gradient descent, randomly picks the global minima, something like that. I thought that it randomly find the best fit line, minimizing the error.
No, but how can you? I mean, that doesn't sound reasonable, right? So how can you randomly choose something and then hope that it is best fit line, right?
No, no, sir, no. By the iteration, after the many iterations, it will come to a.
Oh, I see what you're asking. So you're saying, how do we find the W's? What method are we using to find these W's? That's what
Yeah.
you're asking, right? So
Yes.
I know that the W is the eigenvector corresponding to the largest eigenvalue of the covariance matrix. But how am I going to find this?
Yeah.
Right? So now you're asking, am I going to use gradient descent to find this? Right?
Yeah. Yeah.
Okay. So in principle, you can set it up as, I mean, you know that this is an optimization problem, right? So W1 is just max over all W such that the length of W is 1, W transpose CW. We know that this is the optimization problem, right? So this is, I can say W squared as well, right? So this is a convex set. Um, this is a convex function. So you can do, for instance, projected gradient descent. And if you do that, well, you have to do min and then do minus of this because you are doing gradient descent. You will get W. That is a way to solve this problem also.
Okay.
Now, that is from whatever we have seen in this course.
Mm-hmm.
But if you take a proper numerical linear algebra course, people have found super optimal methods efficient methods to solve this problem, because this problem shows up in so many, practical applications. You won't really do gradient descent to get this answer. You will get the answer if you do projected gradient descent also. Right? So, but then you don't have to do that, right? So you can do something more special with this, the structure of this problem. You can exploit that and then do faster. You can get these eigenvectors in a faster way, right? So that how do you do that is, let's in this course at least we'll just think of that as a black box, right? So there is some method. Maybe it's projected gradient descent, maybe it is not. But then if you give the covariance matrix as input, it will solve this optimization problem and give you an output.
Okay, sir.
Sir, isn't it employed? Is it SVD used, sir? I always thought SVD is what is used.
SVD can also be used for this. So because it is a positive semi-definite matrix, you can do something called as Cholesky's decomposition and so on and so forth. So again, you will kind of exploit all the structure available in this problem to do some fast, eigenvector computation.
Okay. I thought commercial packages or whatever, all the open source and commercial packages use some advanced form of SVD approach to solve it.
So let me, so not necessarily SVD, some smart factorization techniques to solve this. Yes.
Okay.
SVD is one matrix factorization technique, but there are others.
So, sir, for this course, we are using this now covariance matrix.
No, okay. Not for this course, right? So PCA is always covariance matrix. Now, how do I get this W1, right? So I have to solve this problem, right? So I know I am just giving this a name that this is the eigenvector corresponding to the covariance matrix, but that's just a name, right?
Okay.
So if I have to write a code to do this, right? So the name is not going to be useful at all to me. I need to know how to find this. Now, I'm saying there are many efficient ways to find this. For this course, you can think of this as just doing projected gradient. You can start
Okay.
at random from some W, take the gradient step with respect to this, project it onto this ball, and then keep doing it. You will
Got it.
still get this W.
Got it, sir. And sir, I have one more question related to PCA.
Yeah.
Sir, usually, sir, we have high features in the CNN or the imagery data
Uh-huh.
rather than the tabular data.
Yeah.
So, sir, we can use this PCA or also there in the CNNs
Yeah,
or in
yeah.
the
Not CNNs, but in image data, right? So, for example, CNN is a specific architecture
yeah.
That does something else, right? So we haven't covered it in this course, convolutional neural networks,
Yeah.
Which extracts feature from images in a different way,
Hmm.
right? So it is not, it is doing something non-linear also to extract images. What we are doing is a linear dimensional diffraction technique. PCA is a linear dimensional diffraction. If you use kernel PCA, it's a non-linear dimensional diffraction technique. But if you use CNNs or autoencoders and things like that, which you may have seen in other courses or online, so then they would use some other way to do nonlinear feature dimensional diffraction, right? So it's not PCA; it's some other way. But then this in the spirit of the same, in the same spirit, right? So for instance, an autoencoder is one which will take my input and then it will kind of find a representation, phi of x, such that if I use phi of x to again run phi of x is in the okay, so it's not the kernel phi of x. So in this case, it will actually be a smaller, potentially a smaller dimensional. Maybe from R100, you will map it to R10, and then you will again do this is an encoder step. Again, you will do a decoder step to get some x tilde. Now, how can I, adjust this encoder and decoder such that these two guys are as close to each other as possible? Which means that if I have somehow found an encoder such that the decoder will get me back the x, then it means that it's enough for me to use this 10-dimensional representation as opposed to the 100. So that is a different technique that people use as well. So if encoder and decoder are linear, then this method is exactly PCA. But if you make this non-linear, it's called an autoencoder, right? So there are several other techniques that people use in practice. What we have seen is like a very foundational technique, so to say, and these methods built on this.
Got it, sir. Got
Can
it.
I,
Thank you,
can
sir.
I just add one point? Sorry, I just feel compelled to say this.
Yes.
Sorry, whoever asked this question, I couldn't catch the name. See, a lot of times PCA, in reality, a lot of times PCA is just not used for compression or because you have millions of features, right? That is not the only use case. In fact, if I'm not wrong, the bigger use case is a lot of times there are underlying structures you have to uncover, and and it's not about feature, million features or 2 million features. It could be just 100 features, right? But there are underlying structures you need to uncover to do something with it. Like for example, you want to understand what is impacting the brand equity of something, right? Of let's say Coke or Pepsi or any brand. It's not very easy to do that because if you ask people, they will not give you the right answer because a lot of times they don't themselves know, right? So you ask a series of other questions, and with that data, you uncover that structure as to what is affecting brand equity, right? So a lot of times it's about uncovering those structures rather than just compression or things like that, right? And it's very very common in the industry. Like it's like people use it like they brush their teeth all the time. So I thought I'll just share that. Thanks.
Thanks. So yeah, that makes sense. Yeah, any questions? I see two hands raised. I don't know if there are old questions or newer questions. Yeah, Deepak, do you have anything?
Good evening, sir.
Hi, good evening.
Sir, why we are focusing on linear sublevel data, sir, in classification, binary classification?
Why we are focusing on linear? Is that what you're
Yeah,
saying?
linearly supplementable data. It's maybe sir possible data set mapping is not linearly. So how can we deal with it?
Okay. We have seen in the course how to deal with it, but just to, at a high level to quickly summarize, you
So
can.
some real life example of linear sublevel data, so where we use this algorithm.
So real life, you may not necessarily have linearly separable data. So your data is already somehow corrupted or the other in real life. But Pedagogically, if you cannot solve a linearly separable problem well, then how can you expect to solve a non-linear problem with outliers, right? So I think you'll have to go step by step. So the way we start is, if we can understand to solve the linear problem well, can I use the techniques there to solve the non-linear problem? One way that we have seen in this course to deal with the non-linearity is using the kernels, right? So there are two different ways non-linearity can occur in your data set, right? So one is there is a structural non-linearity, which means that the real classifier is not linear but then polynomial. That's a structural non-linearity. The second way non-linearity occurs in your data set is that maybe you have a linearly separable data set, but then some outliers kind of confused your, I mean, kind of broke your linear separability. That's like a noise-induced non-linearity. Now, for both of these, in this course, we have already seen techniques to mitigate both of these, right? So for the structural linearity, we would use kernels. For the noise, to mitigate the noise, for example, in a case like SVM, we would use a specific loss function to do that. Right? So the hinge loss will take care of that. Right? So we have seen this in this course. We have not just looked at linear separable data. Though I would have started always with linear separable data, we would have progressed, right? So either use a kernel method or yeah, I mean, for non-linearity in this course at least we have seen only kernel based.
Sir, okay, sir. And sir, second question is, sir, uh, sir, please explain about why we cannot use linear regression for classification.
Okay. So good question. So I don't know if I covered this in this course. Uh, so so how first of all, let's say how you would use linear regression. I mean, what does it mean to say we are going to use linear regression for classification? And then we'll ask, is this a good idea or not? So if I use linear regression, so I have data which is x1 xi yi, I is 1 to n, and all these are this. Yeah. So all these yi's are +1 or -1. Um, now, if I use a linear regression model, so I can use it because the data is +1 or -1, and my regression can subsume anything, right? So I can use any real value and then still run this algorithm, regression algorithm. That is fine. So I'll get some model H, let's say W in the simple case, right? So you'll get some W from regression. Basically, what I mean is that you send this data set to a linear regression model and out comes a W. Now I have to use this W to make classification, right? So how would I make, what might be the best way to do that? Well, for a new X or any given X, so I'm going to do X transpose W and then look at its sign, and then, I will decide whether this is a positive or negative. This is how I would make the decision, right? Um, so if it is positive, then I'll say y hat I is +1. Otherwise, I'll say y hat I. Now the problem though is, the way linear regression is going to treat uh, what is a good W is not necessarily what we want uh, classification methods to treat what is a good W. What do I mean by that? I mean by this the following, right? So if I take a W and then if I look at W transpose X into Y, so this is my prediction value, and now I'm going to look at the sign of this and make a prediction, whether positive or negative, and Y is actually +1 or -1, which means that if I got the answer correct, this value will be positive. This will, I mean, if I'm predicting negative, this value is negative. -1, this value is negative. If Y is negative as well, then this product is positive. So whenever this is positive, it means that this W predicts this X comma Y correctly. Now, if I write this as a function of W transpose X, what do I really care about? How do I measure goodness of this W with respect to a given data point X comma Y? Well, what I really want to do is, if this value is positive, then I don't want to penalize this W at all, right? So I don't want to penalize this W because this W is good for this X comma Y whenever W transpose X comma X into Y is positive. Whereas if it is negative, then I want to say that I suffer a loss of 1. right? So I can think of this as the loss, right? So now this is the loss that I really care about. When this product is negative, which means that what I predict does not match what the truth is, then I have to suffer a loss of 1. If the product is positive, then what I predict is actually the truth, then I should not suffer a loss for this W. If what I predict is 0, then let's say, I mean, it can go either way, right? So we can, by default, let's say we can set it to either 1 or 0, doesn't really matter. But now if you look at what linear regression does, right? So how does that measure goodness? Well, it's going to measure goodness as W transpose X minus Y square, right? So that's the way linear regression is going to measure goodness, right? So now this value, is Y in this case. If you are running this for a classification problem, Y is either 1 or minus 1, right? So if Y is 1, then this value is W transpose X minus 1 squared, right? So which is W transpose X squared plus 1 minus 2 W transpose X. Well, I can write this as W transpose 2 W trans. So this 1 can be written as, for example, Y squared, because Y is 1, and I can add a Y here. And
Kindly move the book within the camera range, sir.
sorry?
The book is, what you're writing is not really visible. Can you move it? Okay.
Sorry, let me just move the wrong.
Yeah, it helps. Thank you.
Sure. Okay, so the way what I am trying to say is that let me write this again. Right, so this is the loss that I minimize in a regression setup. So this loss when Y is 1 is going to be W transpose X minus 1 squared, which I can write as W transpose X squared plus 1 minus 2 W transpose X. Now the way I'm going to interpret this is I will write, let's say I add a artificial Y square here. Y is 1, so Y square is 1. Now, and I can add a Y here, which means because Y is 1, I can multiply this 1, which means that this whole thing is just, I can write this as W transpose X into Y minus 1 squared. This is W transpose X squared Y squared, which is W transpose X squared plus 1 minus 2 W transpose X into Y, but then Y is 1 in this case, so I can write it like this. Now you can try it out yourself. Even if Y is minus 1, I can write it as W transpose X into Y minus 1 squared. Well, what does that mean? That means that my loss that I really care about is there is a 1 here. If as a function of W transpose X into Y, it's going to look something like this. Right? So whereas what I really care about is this loss, which is, if the signs match between what I predict and what the answer is, I should give a 0. I should treat that W. I should not penalize the W. And if the signs don't match, I should penalize this with the value of 1. But what least squares or regression problem would penalize it, even if the signs match, if the value is large, I still am going to suffer a loss, right? So because Y is 1, if W transpose X is 100, then the loss that this W incurs here is 100 minus 1 squared, at least in my, when I'm running the linear regression problem, right? Because that doesn't know that I'm going to use the sign of W transpose X later, right? So it's going to think of this W as suffering 100 minus 1 squared, right? So, and then trying to find, and then we'll try to find a better W. But then what really is happening is, you're going to use this to do only the sign, right? So, and then look only at the sign. But then, that the linear regression doesn't know that, right? So it's going to treat any W that predicts as 100, but then the actual Y is 1 as actually a bad W. But if you're using sign, it's actually a good W. And so, because this curve is not a good approximation of this curve, which is what you really want to minimize, it's a bad idea to use linear regression for classification. This is the real precise reason, right? So, though we might argue as outliers and sins, so on and so forth, it simply doesn't really minimize what we really want to be minimized. Deepak, I don't know if that answered your question.
Yes, sir. Thank you, sir.
Okay, so last
So
minutes.
I had the question on pseudo inverse.
Yeah.
So in the regression problem, typically, I hope I'm right. Typically, we end up with a situation where we have more equations than features. As a result, you'll always probably end up with the overdetermined system, and there won't be any inverse, so on and so forth. But we still find through pseudo inverse. Now, from whatever I've read, I've understood it basically looks for, among all the W's which can be a solution, it will look for the one which is the least norm, right? Now, how does it actually do it? Because finding the least norm itself sounds like an NP hard problem to me, right? So how does it actually kind of implement and solve is a question which is bothering me.
Okay, so it's not an NP-hard problem because you are kind of trying to find the W with least norm in some subspace, which can be, so you want to kind of say that, find minimum over W, norm W squared, half norm W squared, such that W belongs to some subspace. And this subspace you can define based on your data, right? So this is not at all an NP-hard problem, right? So yeah, so affine subspaces actually. This is one obvious answer to this, right? So you can solve this problem first thing. So pseudo inverses would kind of efficiently implement this. A great thing that happens in gradient design, right? So if you run your overdetermined system least squares problem and then run your gradient descent will actually find you the least norm solution. This needs more optimization, theory to explain why it happens. But this is what is called as an algorithmic bias, right? So people talk about data being biased and so on and so forth. But your algorithm itself can be biased towards picking certain solutions than certain other solutions because of the way the algorithm is set up, right? So at the end of the day, you want to find a solution that minimizes the loss. Now, gradient descent is a specific algorithm that we might use to solve this problem. And if it's an overdetermined system, we can ask which one does gradient descent actually converge to? And you can argue that because of the dynamics of gradient descent, it will always converge to a least norm solution. That's actually a great result in optimization. So that's what typically is called as algorithmic bias. So at a high level, to answer your question, it's not an NP-hard problem. You can do simple gradient descent.
Okay. But algebraically, if I could just dial back, like for example, let's say we have a system of equation, and it's singular, right? For whatever reason, because you have too many equations, and there is it's not full rank and things like that. It could be, let's say, a singular matrix, but we still need to find a solution for that. Let's say, in that case. How does it actually algebraically? How do we think about it? I mean, implementation wise, maybe the gradient descent will find, but algebraically, how does pseudo inverse help answer that, like navigate that situation is where the gap is.
So think of pseudo inverse as an operator. So you have, let's say, a W that solves. Let's say a W that has the least error, right? So xw minus y squared, you want to minimize over W, and let's say there is a W that achieves this. Now, what does it mean to say this is not the only W that achieves this? Well, it means that there is a W plus a whole null space of X set of solutions that achieves this.
Correct.
Right? So this is what is called as an affine space. It's not a null space. It's not a vector space, but then it is pushed by some W. Right? So now we are asking, among all possible points in this affine space, give me the one that has the least norm.
Okay.
Right. So, and that is the one that we will map our, xw to whichever answer. Right. So if I give you xw as some solution, and now if I give you x, and then I want a pseudo inverse, let's say this is b. I give you b, and now I am asking which w should I gave me b, right? So which w satisfied xw equals b, right? So it's not just xw, but then w plus null space of x, everybody would have given me b. Now I have to commit to a single choice, right? So now an operator which maps every b to a single choice, which happens to be the one with the least norm in this affine space, is what we are defining as the pseudo. Right? So
Okay.
that's
Okay.
the definition, right? So we define an operator which, given a B, maps it back to among this affine space that vector which has the smallest norm, right? So now how do you get it? You can do gradient descent, you can do other optimization things, but then that's how you algebraically define the operator.
Okay. Okay. Thank you.
Okay, so we are over 8 o'clock, but if there are any one final question, I can take them.
Sir, I have a broader question regarding what's the main difference between a statistical model and a ML model. Uh, Basically, banks have been using the statistical model like logistic regression for many decades. But when we say that the ML linear regression, is it different? And will a ML engineer give a model which have higher accuracy than a statistical model?
So it depends on the task that we care about, right? So what kind of tasks? I mean, if you mean logistic regression is a statistical model, then it's also an ML model, right? So traditionally, people have used logistic regression, linear regression. I mean, linear regression has been there like from the 1940s, 50s, even before that, right? So what statisticians initially, built, now they less cared about classification problems. Um, and were more interested in regression problems. But now, once classification became mainstay, so now we have the ML. I mean, the lines are blurred, right? So you can say whenever you are using some kind of a probabilistic estimate, the statistician would come and say this is in fact a statistical model. Right? So, but then if you are doing it only based on optimization without really taking course to probability to define a model, then you can simply say that it's like a simple ML model, right? So uh, I think this is just terminology, right? So it doesn't mean that an ML engineer is always going to be better than a statistician or anything of that sort.
But just to add on, so for example, the example Vasu gave regarding the default rate of a customer,
Yeah.
the banks have been using this for decades for logistic regression, and there is always this question that why don't they use some advanced ML models which give you a higher accuracy?
Yeah.
And their major defend point is that they use it because it is explainable. The logistic regression is explainable, and you can explain this to regulators.
Yeah.
But but when we use ML model and some techniques like regularizing, that also improve the accuracy, right? And if somebody who's better understanding that models can also be explained to regulators. So isn't this gives an superiority to ML techniques rather than the plain vanilla statistical models?
So there are two things, right? So one is what do we care about? What do we want the model to do, right? So if we care about performance, but not really explainability, then you could use, let's say, a bagging kind of a model with weak learners or a boosting kind of a model with weak learners, which typically might perform better than logistic regression, because logistic regression is a simple linear model and it can do only so much, right? So maybe your real combination of features that can explain the data is not necessarily linear. Maybe your kernels may not necessarily work that well always also, right? Now, if performance is the only goal, then you should use all these complicated models, definitely. But having said that, in a bank setup, of course, you want to explain to your manager why the particular loan was rejected or given, right? So now, on the one side, increasing the complexity of the model is going to make your accuracy in the test set better and better, hopefully. On the other side, the explainability goes down and down, right? So because the models are becoming more and more complicated. So now this is an active, so to say, area of research now, right? So how can you take a complicated model? Of course, you want to do the right thing in terms of performance, but can you somehow make these complicated model explainable? Now, the moment you bring in explainability, it needs a solid definition, right? So what do I mean by uh, explaining a model, right? So if I say that a model should be explainable to my manager, I mean, what is the model of the manager, right? So the manager's brain, I don't know that, right? So explainability is a very tricky thing. And that's why people are still struggling to say that this is the right way to explain a machine learning model. Now, there are several ways people have come up with doing what are called as post hoc explainability, where you take a complicated model, imagine that just a black box, you give features, 10 different features in a bank setup. Let's say you have 10 different features, and then the black box is a complicated black box, and it spits out an answer. Now, you don't want to explain the black box. You want to explain the outputs of this black box, given that this is the inputs. Now, how can I? One question that people have asked is how can I somehow attribute which features are more important than other features, right? So, if I'm given the black box, can I somehow say in a precise way some features are more important than others? Now, people have tried game theory based techniques. For example, if you're aware of game theory, there is a technique called Shapley additive predictions, explanations. It's called SHAP, which kind of thinks of these features as players in a game, and the output that you get is kind of a coalition value of this game. And now, let's say all these players played together as a feature vector, and then they got this much reward, which is the prediction of the black box. Now, how can I apportion this reward to these players in a very rational way? You can think of this as a separate problem, and then whichever player gets the bigger share of the answer is a more important player, right? So, and that might be a reasonable way to explain to your manager, right? So perhaps, right? So now this is one technique that people use, which is called as Shapley additive prediction, which is a post hoc explainability technique, and there are others, right? So there are several, and then there are people who are trying to come up with models which are inherently complicated but still explainable also. For example, at IITM we do a lot of things here in the labs here at the CS department. We try to build inherently interpretable machine learning models, and what does it mean to do that, and so on and so forth are questions of interest here. Yeah, but this is an active area of research, Manoj. Let me put it that way.
Okay. And sir, just one, when you say explainability, is it explainability towards somebody who don't understand machine learning model, or even within machine learning community, we see them as a black box, as in these models?
Both. So, but these explainability models. So, for example, if you have like a billion parameter neural network or something of that sort, let's say your chat GPT, right? So now your chat GPT, you use your chat GPT and it produces something lousy that you are not expecting it to produce. Then you want to ask the question, why did this produce this, right? So of course you can say the probability of this output was higher, but why was this probability higher, right? So can I understand the internal mechanics of this chat GPT kind of a system better, especially when you have 3 billion parameters, which is as big as the number of neurons in the brain. It is not that easy to do this, right? So even for people in the machine learning community, right? So it is not easy to understand this. All said and done, again, we did not cover deep learning in this course. So deep learning, neural network based techniques which seem to work really well in practice. But our conventional wisdom would say that if you increase the number of parameters, you are making the model complicated, so it should overfit. But it doesn't. In a lot of cases, in practice, it doesn't overfit, right? So even in machine learning community, it is unclear why certain models work as good as they do. Of course, people have given all sorts of explanations, but a rigorous understanding is still lacking, right? So, it is like the businesses have gone ahead and gone 10 steps ahead, whereas the theory is slowly following, right? So we still don't have enough theory to match the confidence with which the businesses have already started applying these tools in real world. So that is again an active area of research.
Okay, thank you, sir. That's helpful.
Okay, I think we can close here. It was great again meeting all of you. Let me just quickly my laptop. Yeah. So I hope all of you had a good course. I think this course hopefully was beneficial to all of you, and good luck for your final exam on 30th. And I hope to see you at some other different course at some other point of time. Thank you very much.
Thank you.
Thank you,
Thanks,
sir.
everyone.
Thank you very much. Thank you very much.
Thank you very
Thank
much,
you,
sir.
sir.
Ganga Prasad apparently has a
Thank you,
question.
sir.
I think he
Oh,
asked
okay.
for
Oh,
last 5 minutes. Yeah.
okay. Go ahead. What is your question?
No, it's fine, sir. Those are very general questions. So if you have other commitment, then we can wind it up, sir. No problem.
No, no, no. Let's finish it. I mean, I will get a chance to talk to others.
Okay, sir. Then these are very general questions, sir, and please excuse me if it sounds very trivial. So the first question is, sir, related to way forward kind of thing. I am from manufacturing industry, sir, and some. Hello, am I audible, sir?
Yeah, yeah. Go ahead.
Yeah, and some exposure in not some exposure also in business excellence tools like TPM and Six Sigma and all, and that is one of the reason why I got into this course. So could you please give us some insight about the application of data science in manufacturing industry, in operations mainly, one part, and related to that, uh, in this course, sir, the course has been designed like this that many other courses related to data science are placed in degree level, at degree level, right? So before getting into degree level, we'll have to go through one more diploma that is related to programming. It means it is nothing but a delay of one year, because it will take one more year to catch up with those topics. So, what can be the approach for people who are slightly more inclined towards data science than programming?
Okay. So, okay. So I don't know if I am the best person to answer at least the second question, but with respect to the first question, I'm assuming that manufacturing or operations research kind of setups, you would have a lot of demand forecasting or quality forecasting and things like that, right? So supply chain optimization kind of problems, which can be thought of as optimization problems. I have not worked in specifically in any of these, but I would imagine that I know for a fact that a lot of MLB is being used in manufacturing. Right? So there are people here at IIT, faculty at IIT who I often hear use a lot of ML for manufacturing analytics. The precise nature of the problem, maybe I think being a domain person, you should be able to figure out. Right? So I think if you ask the question, are there places where you could do prediction of certain things, right? So which is the right place to start, and then ask if there is anything like that in your own work. You should be able to figure out a lot of problems.
So in supply chain, hardly we come across a kind of problem related to classification and all.
Okay, so for example, in supply chain also, you may want to make some decisions as to how you manage your resources to how you allocate your resources and things like that, and based on how you allocate your resource, you might get some feedback as to you know uh, whether whether it worked, did not work, and how much time it took. Simple example may not be supply chain, but then let's say you want to transport certain amount of items from one place to another, and then there are multiple ways you could do this, and then you as an algorithm decide one way to do this, and then you get some feedback as to whether how much time did you have to spend to transport certain amount from a source to a destination, and then you want to change your model in which you are making predictions as to predictions that can be used to alloc. So I don't know if this is exactly matching what you have in mind, but there are definitely a lot of operations research related questions that
So,
fall in
sir,
that.
like you are mentioning the name of operations research couple of times. So, does it mean that people who are from operations, I know there are a couple of more people in this group who are from operations. So should we explore opportunities, or should we explore any good course in operations research to take our journey further?
Okay, so that depends on what is your passion. Yes, operations research is your passion. I'm sure there is. So there is a
Passion is
department.
towards passion is towards the numbers, sir. That's why we got inclination toward this course, right?
Yeah, yeah. The passion is towards numbers, right? So anywhere where if you want to make reasonable decisions, you want to convert it into numbers, right? So that's the only way you can make decisions. And these course, whatever algorithms you learn in this course are going to be useful there. Right? So definitely,
Operations research can be one of the options to explore.
yeah.
Okay, sir. And sir, my last question. I know, sir. Before asking this question, I'm cutting a sorry figure. Please excuse me if it sounds bad. Sir, like we talk about statistics and we talk about ML model, right? We have seen that all these models are based on certain assumptions. Like every model starts with some assumptions,
Mhm.
and in the same way in statistics also, while calculating MLE and all, we have seen that in case of normal distribution it was percolated down that it is nothing but the sample average, correct? It is nothing but the sample average. And in the same way, in hypothesis testing, we also came across the concept like confidence level and all. So one of the observations which I have seen that my decision or our decision change a lot based on sample size, and if we are not meeting the assumption, because in real life it is very difficult, difficult. Almost I can say that next to impossible that all the assumptions are in place, intact, the way it is given in academic field. Then how can I rely on my prediction or analysis? I know it may sound very trivial, but I am really looking for answer to this question. That's why I thought to bring it on the table.
So there are two things to look at here, right? So if you in practice for a lot of problems, you might have huge amounts of data, whatever they are calling as big data. Right? So if you have a lot of data, then even if you start with the poor assumption, let's say some prior assumption about your classifier or your model parameters, so on and so forth, the data will kind of dictate what you really learn. So if you have large data, then these assumptions being wrong or right is not that much of a problem because your algorithm will adjust accordingly. When you have less data, but then you still want to do well on something that you don't know, uh, then you have to rely on some assumption or the other, right? So otherwise, your data, I mean, your assumption can be thought of as a pseudo data in some sense, right? So again, in a direct way. And all we are doing here is kind of saying that there might be some reasonable ways to do these assumptions, which seem to have worked in a lot of cases in practice. Right? So, but if you have very less data, only 10 data points to deal with, and you don't know anything about the data, then it is highly unlikely that you are going to get a model which is going to do well in practice. That's the reality, right? So somehow you need to understand the space where you are trying to make decisions, and it is not magic, right? So that you either should have a lot of data or you should have good assumptions. These two, without both of these, no method is going to work.
Because like in for hypothesis testing also, the moment I change my confidence level from 90 to 95% or 95 to 99%, my decision goes 180-degree opposite, right? So if we compare it with pure science like physics and chemistry, where if some rule has been established, then it is there forever. So how to rely on this kind of model? So that that doubt keeps coming to mind. So
Yes.
before taking any big business decision, how to rely on this
Yeah,
output?
yeah. So when you say physics, right? So there is an underlying law that always is true.
Right.
For example, right? So if I'm throwing a ball, I am measuring just, I don't, let's say I don't know anything about physics, right? So I throw a ball with certain force and then it lands up somewhere, right? So now I just feed this as a data to my model and I want the model to recover the physics, let's say, right? So if I want the model to figure out the Newton's law from data, now with just 5 data points, it's very unlikely that you are going to, you know, recover Newton's law. But if you have a lot of data points, then it's highly likely that you will recover, assuming you are searching in the right space for the solution. So you need more data, right? So if you're taking a business decision, then and if you want to really be confident about that, then you can really be confident only if you have a lot of data which the model has actually worked on. Or if you're very very sure about yours. Again, I'm going back to the same thing, but that is something inevitable is what I feel.
Sir, in this, that's just a follow-up question to this only. In this course itself, there have been many places and occasions when you have said that this is beyond the scope of this course. This is beyond the scope of this course, right? For many people like me and others in the group, like like what can be the other course? Because after now it's a 4 years BSc, right? Now, and as per new education policy, one can directly go for PhD after this course. So, what is the other source like to cover those, at least for enthusiast people like who are enthusiastic to learn more about data science? So what should be there actually? That was in fact my inclination when I asked that question. Also, how to cope up with other courses like deep learning and all, which are in degree level, and we will have to wait at least for 1 year or 1.5 year. So, so I'm talking. I'm just clubbing these advanced topics also with that. So, could you throw some light, like some good books or some resources, so that because now time is a constraint for most of us.
Yeah, sure. Yeah, of course, you have a lot of MOOCs, deep learning MOOCs, right? So, I mean, I'm sure even the online BSc ones are already available on YouTube. You can start looking at them, right? You don't have to wait till the degree level to start looking at them. Definitely one thing. And having said that, I think it's a good idea to open a book at some point. So, if you are the old school type, you should definitely look at some nice textbooks which cover whatever we looked at in this course and much more elaborately. Maybe something like Christopher Bishop's pattern recognition and machine learning, like the Bible of machine learning, right? So, at least classical machine learning. You would find a lot more topics than what we covered in this course in a lot more detail as well. So, if you are enthusiastic to learn more, that is one way. Now, again, if you're enthusiastic to learn more in the theory aspects of things, then there are other books that I can suggest. In the practical aspects of it, then you can go the deep learning way or the sequential decision making way, where you learn. You're not given all data at once, but then data comes in one by one. How do you cope with such situations? There are some books for that as well. Uh, yeah. So I mean, please write to me, and then I'll send
Okay,
you.
thank you, sir. Thanks a lot for valuable time. Over to you, Ravi. Thank you, sir. Thanks a lot.
Yeah. So the question is probably an extension or a variant of what Ganga Prasad has asked, but my problem is a little different. I entered as a diploma direct entry, and I would like to actually convert it into a BS. I was told that I can take the exam and do the entire thing again, and I will have to repeat the data science part again. That is not something which is put me time efficient. Let me put it as I'll be repeating 1 year of the entire thing, which I already did. Is there something which is being thought about for students like me? Because I heard that there are other students also. I've not seen them in any forum or anything, but I would be really interested in converting. I don't mind doing the foundation. I have my engineering degree and experience and everything, but foundation, if I have to do it, I don't mind doing it. But doing this again is going to set me back. That's the only thing that I have as a request. That is there something that can be done?
Yeah. So I totally hear you. I can I can raise this with the concerned people here in the online BSc team. Uh, I mean, with my capacity, I cannot really give an assurance at this point what would happen, right? So
Sure,
because
sure.
I'm not part of the managing board for this group, but I'll definitely talk to them to see if there is a way to do credit transfer or something like that, if that is possible, especially because you've done this course here already. I'm sure that something like that will be worked out, right? So, but I don't want
Thank
to
you very much.
give a word.
I mean, I understand, but if something can be done, because if you want me to write the entrance test again, I'll write it. Want me to do the foundation, I will do it. But this 1 year is something which is precious. I mean, I'm 50 minus. Let me put it as I'm not 40 plus, so I'm 50 minus. So it doesn't make much of a uh, time sense for me. That's the only thing that I have as a concern. A decade back, perhaps I would not have bothered at all. I would have just simply said, "Yeah, let me do it again."
No, makes sense. I'll just raise this concept.
Thank you, sir.
So,
Thank you very much.
so adding to
Thank you.
that question, so the courses like Introduction to Big Data and Deep Learning, sir, yeah, I also interested in their that courses because I'm the student of this DAD only in data science, like Ravi.
You're student of what?
Sir, yeah,
Like me, he's also a direct entry, but he wants to do the deep learning courses because, as we understand, we have to go through the programming diploma for going to that course.
Okay, it's the same
So,
concern basically.
yeah,
yeah,
same
yeah.
concern. If I have to go, then I mean, like going through the programming part, that's not a concern at all. I'll do it, gladly do it.
Yeah.
But repeating this part is where I'll be again setting myself back.
No,
That's all.
I understand. Okay. So have you got clarity on this from the management how they are trying to do this, or
Close to some 9 months back, there was a session by Professor Tangaraj here, and I asked him the same thing. I was that point of time in the first time doing my maths and stats.
Yeah.
So sir said I'll have to repeat, and I was like, sir, please try something which is going to set us aside, because I didn't actually discontinue and then go for the full thing. I continued because it makes more sense to me if I continuously do all these things, because they're falling in a sequence: math, stats,
Right.
MLF, BDM, and now MLT and MLP. They're all falling in a sequence. So disturbing the sequence is not what I want to actually.
Yeah. No,
go
I
for.
understand. Yeah. So I mean, so a lot of things have also changed in the program in the last 9 months, right? So for example, it became a BS now, and so on and so forth. So
Yeah.
I'm sure they'll relook at this. I'll anyway talk to them.
Thank you, sir. Thank you, sir.
One more thing adding on to that, sir. I spoke to instructors, not instructor in the orientation program. I think last orientation program. So somebody there told me that this thing is under the carpet. It is not officially, but this thing they are discussing under the hood, and they don't know whether they will do this or not. What I heard about from
I
the
have no clue, Rohit, about
okay.
what is the discussion, because I'm not privy to it or I'm part of it. But what I can do from my side is I can definitely raise this as a concern that you have raised here, and I let the management do whatever they.
It's more of a request, sir, because it'll be. I mean, we'll be. I'm sure Rohit also is on the same boat as I am. We'll be glad to
Yeah.
complete it.
Yeah.
I'll write the exam, and no worries there. I'll do the foundation, no worries. Just this 1 year, just I want to catch a break here. That's all it
Because
is.
sir, I saw the syllabus for the big data deep learning. It is quite impressive, sir. Literally, the faculty and all the thing outside. It is there's nothing like this outside.
Sure, Rohit. I hear you. So I'll do this. I'll talk to them.
And how may we contact
Thanks
you,
a
sir,
lot,
or
sir.
how will you disseminate this to us back? Is there some way we can?
So I can, yeah, you can just drop me an email. Once I get some clarity on this, I will respond to you.
Sure, sir. Sure, sir. Thank you very much. Thank you.
Thanks a lot, sir.
Thank you,
Thanks
sir.
a lot.
Thank you, sir.
Thank you very much for spending more time than you promised. Thank you very much again. It was a pleasure
Thank you, sir.
doing your courses and watching your videos. Thank you.
Hope to
Thank
see
you.
some other questions, sir. Yeah, okay.
Definitely looking forward to in the future. Thank you.
Thank you. Thanks,
Have a
everyone.
nice evening. Bye.
Thank you.
Bye, sir. Bye. Thank you.
Thank you, sir.